Good morning everyone. In this video, I am going to present some of the antenna parameters like polarization, field lenience, gain, and Frisk transmission formula, and what is the radiation resistance. See, polarization is the main important parameter for the antennas while it is transmitting and the receiving. When the transmitting antenna and receiving antenna are both polarized in the same orientation or same direction, you will receive the maximum power. If the antenna transmitting antenna is vertically polarized, if the receiving antenna is horizontally polarized, minimum energy will be received by the receiving antenna. If the receiving antenna is also vertically polarized, then you will receive the maximum signal from the receiving antenna. So this is the polarization is the curve traced by the end point of the arrow, that is the vector representing instantaneous electric field. That is the always polarization is the orientation of the electric field, not the magnetic field. You remember always this is the how it is pointing the electric field, that gives the direction of the polarization. The field must be observed along the direction of propagation. How it is propagating the direction of the electric field. See, this is the how the wave is rotating at the electromagnetic wave is propagating through the free space. This is at the time bound. It is how it is rotating the tip of the electric field. Always you have to refer the tip of the electric field. This is the general definition of the polarization. This is the elliptical polarization. The tip of the electric field is forming the ellipse. Ellipse, you have the major axis and minor axis. The major axis is this direction, that is the long compared to the minor axis. The major axis length is OA and minor axis length is the OB. That is with reference to the x and y axis. X naught is the coordinate for this one, EY naught is the coordinate for the ellipse directions. That is, it is in the x and y. The axis ratio, that is the ratio of maximum to the minor axis. It is the ratio of magnitudes of major and the minor axis defined for the electric field vector only. That is the tilt of the ellipse. If the elliptical axis ratio is greater than 1, and for the ellipse axis ratio is greater than 1, for circular polarization axis ratio equal to 1. There is no minor and major axis. You have the both are the same. The minor axis and the major axis both are same for the circular polarization. So axis ratio is equal to 1. See here you can see the linear, circular and elliptical polarization. You have the three types of the polarizations. That is, as the time is progressing, if the electric field vector is pointing in the same direction, that is single direction, then it is called the linear polarization. It can be polarized in the x direction or y direction, or it can be any angle with 45 degrees with respect to x direction. Whatever may be the direction, it is same for the linear polarization. As the time is progressing with respect to time, you have the same direction for the electric field. That is circular polarization. It is, you have the two fields in the circular polarization. If the wave is propagating in the z direction, the electric field for circular polarization, you have the two fields x and y. You have the two fields x and y. These two fields are orthogonal to each other. You have the same magnitude. Phase difference between these two is the 90 degrees. X and y are the same. The magnitude is same. As the time is progressing, the tip of the electric field is tracing the circle. And in the elliptical polarization, that is Ex plus Ey or Ey plus Jx, depending upon the right hand or left hand polarizations. That is right hand polarization or cross circle means with respect to time the electric field is rotating in the clockwise direction. In the anti-clockwise or left-hand polarization means with respect to time, the electric field is tracing the left hand or anti-clockwise. That depends upon the orientations of the electric and the magnetic fields. Elliptical polarization, the tip of the electric field is tracing the ellipse. In this one, you have the electric field and magnetic field. The phase difference between them is 90 degrees, but the magnitudes of Ex and Ey are different. The magnitudes of Ex and Ey are different in this one. Here also you have the right hand and left hand polarizations. For the right hand, it is clockwise, left hand counterclockwise. Depends upon the phase difference between the X and Y. It is a phase difference between Ex and Ey. If Ex is leading compared to Ey, then you have the clockwise, or if Ey is leading the Ex, then you have the anti-clockwise direction. This is the different types of the polarization. Mainly we'll use the circular polarization for the ANA purpose. చూడండి oriented along the same straight line at every instant of the orientation is same at each and every point. You have only one component, two orthogonal linear components that are in phase or 180 or multiples of 180 out of phase. Here you can have two 180 degrees components. See, circular polarization, the field vector at that point is tracing the circle with respect to time. It is a function of time. You have the two orthogonal linear components. Here it is the Ex and Ey. Two components must have the same magnitude and have the time phase is odd multiples of 90, 270. Like that you have the phase difference between the two components, right hand circular and the left hand circle. That depends upon the phase difference between Ex and Ey. Elliptical polarization, here also two orthogonal linear components, Ex and Jy, like that, and they have the two components can be of same or different. Here you have the different magnitudes. The two components are not of the same magnitude. The time and phase difference between the two components must not be zero or then you have the linear. If they both have the same, then you have the circular, that the phase difference is 90 degrees. See, what is meant by the copolarization and the cross polarization. Here in the copolarization, the antennas intended to radiate in the same direction. Polarization of the antenna is intended to radiate or receive, then you have the copolarization. Then when the cross polarization means the polarization is orthogonal to specified polarization. If it is same, then you have the cross. If it is orthogonal to the specified polarization, then it is called a cross polarization. See here, the electric field and magnetic field are orthogonal to each other. This is vertically the electric field, horizontally the magnetic field. Always when the wave is propagating, electric field and magnetic fields are orthogonal to each other. See, this directory is very important parameter for all the antennas. It is a function of direction in which the antenna is radiating. It is defined the radiation intensity of antenna in the direction to the near mean direction intensity in all the directions. That is taken as the parameter directivity. 1 by 4 pi into 0 to 2 pi, theta is phi is 0 to 2 pi, theta is 0 to pi, function of theta phi square sin theta d theta d phi. It is in which direction your antenna beam is radiating. In that direction only we will define the directivity of the antenna, and that is maximum compared to the in all directions. The gain also, it is maximum in the main lobe direction. It is the ratio of maximum radiation intensity in a given direction to the maximum radiation from a reference point produced in the same direction with the same power. This is defined gain equal to in terms of the directivity. The efficiency of the antenna is maximum in the major lobe direction. What is the total power radiated divided by the what is the input power you have given to the antenna. That is main efficiency is maximum when it is antenna is radiating the maximum power. That is effective aperture or area. This is main important. What is the physical area and physical length is different from effective aperture and effective area. It is a ratio of power received at the antenna load terminal to the power density of the incident wave. That is, whatever power it is incident, it is not going to the antenna terminal. This is effective aperture is lambda square by 4 pi into gain of the antenna. See, radiation resistance, that is a resistance or the impedance. We can define as a radiation resistance and the loss resistance. The power which is dissipated in the radiation resistance is the power actually radiated by the antenna. How much power it is radiated depends upon the what is the radiation resistance of the antenna and the losses. It is how much power it is radiated determined by power actually radiated and the loss. Power lost within the antenna. This is due to the conducting wire or dielectric properties of the antenna. The main loss resistance or the radiation resistance, it depends upon the dielectric properties of the antenna. And in the same way, effective length, it is different from the effective length. See, this is the length indicates how the antenna is effective in transmitting or receiving the electromagnetic energy. Physical length is different from the effective length. See, there are three field regions for the antenna nearby. One is that depends upon the maximum length of the area of the antenna. That is reactive near field region, radiating near field region, or it is also called the Fresnel region. And third one is the far field Fraunhofer region. These are the three antenna regions surrounding the antenna. That is for the generally we will take the far field regions for the far field regions. When R is less than 0.62 square root of d3 by lambda, then it is called the reactive near field region. D is the maximum dimension of the antenna. Lambda is the wavelength. That is in this field region, the energy is oscillating between forth and back. Next one is the radiating near field region. In this region, the field of the antenna between reactive near field and the far field. This is in between far field and the reactive near field. This is the inner boundary is 0.62 square root d3 by lambda, and outer boundary is r equal to 2d square by lambda. In between this region is called the radiative near field region. Then far field region, that is greater than the 2d scale by lambda. In this region, where the angular the field distribution is independent of the distance from the antenna. It is mainly greater than the 2d square by lambda. See here in the to increase the radiated power, you have to, for the transmission line, you have to, this is the generator and this is the transmission line, and this is the wire is flayed at the ends. This is the generator or transmission line. Or it is also got the guided wave or one dimensional wave. This is the transitional, or it is called the antenna. This is the free space. While it is emanating from the generator to the transmission to go free out, the antenna it should be flared out at the open ends. It should be flared out at the ends. So the wave is going out like a loops. The wave is going out like loops. This is the E field region. This is from how the dipole is constructed. This is the transmission line. This is how the dipole antenna is constructed. That is, two wires are flared out. This is the antenna impedance at the terminals. Thank you.